So we're going to start with number 5 here. 5 I had as one that I would do a force diagram for. Because I've got this fixed charge, in my case negative. Is everyone's charge negative? Yep, okay. It's fixed at the origin. Where must an electron be placed in order for the electric force acting on it to be exactly opposite its weight? And for me, the reason I want to do a force diagram on this is I'm like, okay, they're asking for placement, but they're saying the electric static force being opposite its weight. So that, thinking about that directionality, I think a force diagram is going to help me on it. All right? So that's why I did it this way. I did it with a force diagram. Ooh, I probably should have opened the equation sheet. All right, so I'm going to place my charge here, and I'm just going to label it as negative. And then, see, the weight, the gravitational force, which is the weight on the electron, is going to pull it towards the center of the Earth. So I'm going to place it above it, and I'll just label that the electron. And then the forces on it are going to be its weight, F sub g. And the force, I'm going to call that force sub E for the electric force, or electrostatic force. All right? There's my diagram. That would get full points, because it shows the situation, it shows the forces on my chart. Now I could also put forces on the stationary charge here, right? Not needed, because the thing I'm interested in is the electron. All right? Good? Remember, I only have to do forces on the things that I'm interested in. So, that leads me down to my how. And in my how, send that page again, I would start off with, I'm going to start off with a couple of physics equations. Equals 0. Sum of the forces equals 0. Kind of a base equation. I'm going to look at my equation sheet here and realize there's two. I need to specify the two forces, which would be the weight, or the force of gravity here, and also the force due to electrostatic force, which is right down below it. So those two right above and below each other. I'm going to write those down at the beginning so I don't forget them. F sub g equals m little g, and F, which I call electric, is K Q1 Q2 over R squared. Oh, I didn't put R in my diagram anywhere, did I? That would be R, the distance between them. All right. Remember, if it would help anyone, I can broadcast out to the sides. And there's some factors I need, but so my forces are, which way do we want to call positive, up or down?
Up.
Up?
It says up.
Oh, it does say up? Okay. Oh, I didn't read it. Thank you, sir. So we're calling up positive. That means I have negative weight plus my force electric. This is right from my diagram. Those add up to equal 0. So my electric force, electrostatic force, must equal the weight. Now, some people would mistakenly say, oh, that must be true because they're a force pair. Are they a force pair? No, because think about they don't satisfy the four criteria. Are they the same type of force? No. Are they on different objects? No. Are they opposite in direction? Yeah. Are they equal in magnitude? Yeah, but they failed 2 out of the 4 tests, so they can't be a force pair. Alrighty, so now really it's substitution in, right? Okay, Q of my negative charge on my electron, whatever R is, equals the mass of the electron and the gravitational field strength on the Earth. And I'm looking for R, right? Yeah, so now I just substitute in and solve for R. Because I know K from my equation sheet here. I have the value of little g on the Earth. I have K right down here. I've got the mass of an electron right here. I've got the charge on an electron, which I know is 1 quanta, which is right here. So now it's filling in values. Let's see. 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Q on the negative, I think that's given to me. Oh, they gave me all nice facts also. Negative 0.41 little nc. What does that little n stand for? Let's check our handy dandy equation sheet. Oh, look, a little n. Nano. 10 to the minus 9. Cool. So 0.41 times 10 to the minus 9 coulombs. I know the charge on electrons is 1.602 times 10 to the minus 19th coulombs. I don't know what R is. Notice I use the absolute value of those. Mass on electron, 9.11 times 10 to the minus 31st. 31st? Oops. Kilograms. G on the surface of the Earth, 9.81 newtons per kilogram. Now I'll let you do the algebra. All right, so on to number 6. And I think this one, you could do a force diagram as part of it, but I think this is more, you can just use a traditional Y on this. Diagram might be helpful, but I don't think a force diagram really tells us a whole ton. Because you've got a charge here and a charge here, and they're both positive, which means they're going to have an electrostatic force on them outwards, and those two are part of a force pair, and then they tell me my separation. 0 for me, 0.270 meters. Right? I might start with like the forces are part of a force pair. The forces are created by the amount of charge looks like paint by this point. The greater the separation, the less force. I think that's everything. I think that's a decent Y. I mean, I could probably go in there that the forces are repulsive because they're light charges. That'd probably be good. The forces are repulsive due to the type of charges. Types of charge. The fact that we have two positive charges. How many people had something like that for their Y? Good, good. That's what I would expect for a full credit Y. Showing all that understanding. Alright? Oh yeah, your test corrections are back over in the bin if you guys want those. If not, you can leave them there and they'll eventually disappear. Alright, on to the how. So, should start with a valid force equation. Alright. And let's see what they tell us. They tell us we've got 2-point charges. Q2 is greater than Q1. Total charge on the system is this. Oh, so that would be good to... I'm going to write that down. Let's see, so I have that. Q1 plus Q2 equals 69 microcoulombs. So Q1 plus Q2 equals 69.0 microcoulombs. Electrostatic force magnitude 76 newtons. That tells me F is 76.0 newtons. And they tell me my separation, 0.27 meters. Seven? Yep. Alrighty. Oh, so I know lots of things. Yeah. Substituting in. Oops, we're going to run out of room. Move this all over. Times Q1 and Q2 over 0.
On a test, where you want us to write.
Yep. Yeah, when you substitute in, you should substitute in, yeah. Because if nothing else, it lets me know that you understand that, so that's not where if there was a problem, that's not where it is. If you used 9 times 10 to the 9th rather than 8.99, that'd be fine. Alright, hey, cool. So I know this equation, which has Q1 and Q2 in it, and I know this equation that has Q1 and Q2 in it, so I can just solve, right? 2 equations, same 2 unknowns, algebra. I'd probably personally do it through something like Wolfram. I'd go and put those 2 in and separate them by a comma. That way, it would solve for me, right? But you can do the algebra, you can do substitution, solve one of the two equations for, say, Q1, substitute it into the other one, and you'd find Q2. Then you can substitute that back into the original, and find Q1. So whatever algebra you need. Does everyone know how to do the algebra on that now? All right. Let me know when you're ready to move on. We'll do number 12 next.